All right, so let's take a moment and look at a little closer at our logistic equation, right? At the equation that describes the growth of population um, with with a carrying capacity. All right, and so that looks like this right here. Right, and so this describes a population living in a situation where there is a limit to how many individuals can occupy that space. All right, so as an example, let's look at one with a specific example. Dx dt equals, let's go with 4x minus x squared. And if we look at that, we see that that is a logistic equation. Technically, the carrying capacity would be 4. We see that 4 occupying, whoops, not that one. Let's try this one. We see that 4 occupying the space of M, the maximum. Okay. Now, let's first talk about, let's introduce an idea here. Let's introduce the idea of critical points, critical values. And these are quite simply the zeros of the right hand side. All right. Now we ought to mention this as well. Well, let's put this here. So these are the zeros of the right hand side of the equation. Now this particular equation, these logistic equations, are what we call autonomous. I don't know if we've used that term in here before. Autonomous. And so if we look at this, we see that x is the function that we're after, right? It's the function that we would like to find as a solution. T is the independent variable, right? But notice, what makes them autonomous is t does not show up in any of the terms. So you don't have a plus 6t or a 4xt. There are no t's over here. So that's what makes it autonomous. And so those are the kind of equations that we have this discussion about with critical points and later with equilibrium solutions and things like that. So let's talk about what it means to be the critical points. And this is pretty easy for our particular example. We just simply take our right hand side to find the critical points, set it equal to 0 and solve. And that's going to give us two values. Don't do that. And so that gives us two values. X equals 0 and x equals 4 are our two critical values. Now, what do those mean? Well, the first thing to notice is those are actual solutions to the differential equation, right? If x equals 4, you take the derivative of that, that's 0. And then you go 4 times 4 minus 4 squared, that's 0. So 4 is a solution, all right? So these critical values are solutions themselves, and of course these are just constants, right? These are just constant solutions or horizontal lines. But what really becomes interesting is when we start looking at the slope curve of this, right? The slope graph of this. So let's I've added this to our Canvas page. If you go to Canvas and you go to more resources, this is still a work in progress, so it still needs some improving, but you might find it helpful. You can still jump into GeoGebra and use GeoGebra and use all its functionality. But if you just need something quick, like we're going to use here, let's see, make that a little bit bigger. This just quickly creates a slope field, and it also graphs solution curves for a given initial condition. So you can see the little point here is the initial condition as illustrated right there. this is not our, this is a different differential equation, but I can if I change the initial condition, I get a different solution curve. So you can imagine all of these curves graphed on this function if you want to see. But you see how these curves fit the slope field. But what I was saying is, what we want to look at is, we want to look at, see if we can enter this with little to no trouble, or lots of trouble. So let's look at the slope field of 4x minus, nope, minus x. I'm having to enter this on a kind of a pain of a keyboard here. So now I gotta find. All right, there we go. Oh, we got to talk about this for a second. This is a little tricky the way I've got this set up. So our differential equation, ignore what you see on the screen. Our differential equation was dx dt equals 4x minus x squared. So let me write it down. Right, so I just mentioned this because you're going to see this in this section, and it might catch you. When we go to graph things, we're used to graphing on the x and the y axis, right? So an equation that comes to us in this form, we don't want to type in dx, we don't want to type in 4x minus x squared. We want to realize that this is the actual, if we put this in xy notation, this is the actual thing that we want to work with when we type it into, say, Desmos, because Desmos works on x and y, the x and y axis. So just make this little translation. Although for population equations, we usually let x represent the name of the population equation, which is a function of t, and that's why you see dx dt. So make that little translation so that you can type this into anything that is graphing this for you. Alright, so let's try that again. So 4y minus y squared, and if we hit enter, you can see, you can just double check, y prime equals 4y minus y squared, and right now it's set up for to find the solution that has this initial condition that goes through the point 0.81 1.25. That doesn't matter. What we're looking at is the slope field, right? And the first thing we're going to look at with the slope field is, remember our critical values. Our critical values were 0 and at 4. And look, at 0, or sorry, yeah, let's go to 0. At 0, all of these curves come in. And in fact, if you could zoom in on this applet, like I say, it needs a little improvement. But you would notice that at 0 itself, you've got all these horizontal slope splines, indicating that there's a curve that goes right through there. In other words, the x-axis, or y equals 0, is a solution. Okay, so that's one thing that we find with the critical values, that horizontal line will be a solution. And again, look at 4. That horizontal line would be a solution, right? As we mentioned, 0 and 4 are solutions. Okay, that's one part, and we see that with the slope field. The other thing to notice is, no matter where I start my initial condition, let's do this realistically. Remember, so this is a population. This is supposed to be describing a population. So we're talking about being only interested in time starting at 0 and moving forward. So starting right at the origin and moving this way. So we can kind of ignore quadrants 2, 3, and 4. We just want to work in quadrant 1, right? And this function, this solution behaves like we would expect. If our initial population, the population at time 0, is 1.8, our population is going to grow and grow and grow until we hit our carrying capacity of 4, and then it's going to just kind of become asymptotic there, right? Doesn't matter where we start at time 0, the population grows and grows and grows till it hits that carrying capacity. But by the same token, if I start above the carrying capacity with more rabbits on the island than the island can support, their population will decrease. They will die off until we reach that carrying capacity, and then it'll level out. So it's nice to see the confirmation of our simple model in this graph, right? All right. And it you know, for some reason, if at time 3 we started at 2, we still increase until we hit our carrying capacity, right? Okay, so those all match our what we would expect with a logistic model with a carrying capacity. But here's what we're going to focus on. Look at the entire solution here. Okay, so look at the entire solution, and I'm just going to move the starting point around, indicating different solutions with different starting points, right? Look, no matter where I move my starting point in here, I get a real similar behaving curve as a solution. In particular, the curve starts off close down here at 0 and then eventually leaves it. Okay, eventually leaves it. All right, we call that an unstable solution. We say that this critical point is unstable because the solution leaves it eventually. It may stay close for a while, but it leaves it eventually. So that's an unstable critical point. But look at our solution up here. Now it gets sucked into this solution. It gets closer and closer, and it never leaves it. And it doesn't matter what my initial condition is. If it's in this little zone, I leave the unstable critical point of 0, and I become asymptotic to the stable critical point of 4, right? Now, so we say that 4 is a stable critical point, meaning that all our solutions eventually go there. Look, when I start up here, look at my solutions. They eventually go to 4. So it's a stable, and they stay close to 4, right? So they don't wiggle around. So that's a kind of a qualitative property. Even if we have a differential equation that we can't solve, we can look at the slope field and start to see these stable solutions. This would be an equilibrium solution, right? That's where the population reaches equilibrium. It's no longer changing, increasing greatly or decreasing greatly. It's equilibrium. Also, no matter where I start my initial point, 0, the solution eventually leaves 0. Okay. All right. So those are some characteristics of finding critical points. So the critical points are the places where the right hand side equals 0, but they represent the equilibrium solutions for our equation. So our solution may be doing all kinds of things, but eventually they'll come in and they'll become asymptotic and get close to the equilibrium solution, and that's where, you know, the system reaches an equilibrium, reaches a balance. So we use some fun terms here. This is kind of a funnel, right? All our solutions get funneled into this. This solution we kind of refer to sometimes as a spout, because the solutions, you know, may start there, but eventually they get spewed out. Doesn't matter where we start. Okay, I'll just mention this. This little applet here is quite handy because it illustrates, you know, some of the power of GeoGebra. But I want to point out, GeoGebra actually solves this differential equation. Now you solve this differential equation yourself. We know how to do it by separating variables, but just if you need a little help, GeoGebra also offers that assistance. All right.